So in this lesson, our goal is to thoroughly understand the principles of potential energy and kinetic energy. Now, before we talk about potential energy and kinetic energy, if you're looking for the solution to this problem that you're seeing on screen, then please check out the timestamp below to see where the calculations start. Because at the beginning here, I intend to dissect the principles for those who want to build up a conceptual understanding. But if you're just looking for the solutions, then please check out the timestamp to see where the calculations start. Now, before we talk about potential energy and kinetic energy, it's very important for you to understand also something called mechanical energy. Now, all mechanical energy refers to is just having the capacity to do mechanical work. So the principle is sort of similar to potential energy, where for potential energy, it's just the energy that is possessed by a body by virtue of its position relative to some datum. And we're going to look at exactly what that means. Whereas for kinetic energy, it's the energy that is possessed by a body by virtue of its motion. So one is more static and the other is not. So if we talk about formula now, then for potential energy, you will often see this version, which is mass multiplied by gravity and multiplied by height. Whereas for kinetic energy, you will often see this version, so that's half multiplied by mv squared, where m represents mass and v will represent velocity. Now, as a conceptual understanding, you will often come across something else called, or a topic called, conservation of energy that's linked to potential energy and kinetic energy. And because we can't create energy or destroy energy, if we have some potential energy, so that's static energy with a reference datum, and I'm going to sketch that for you in a second, then what's going to happen is we'll have a constant movement of energy flowing between potential and kinetic. So you'll have the same energy being dispersed as potential energy and kinetic energy. And what that means is at any point, if we were to sum up the potential energy that we have plus the kinetic energy that we have, then we're always going to end up with a constant value. Meaning we will keep getting the same end result. And that constant value, it often represents the total energy. So you can also see this as the total energy. Now I'm going to show you exactly what that means now using a side diagram, and then we're going to come back to the calculation here. So let's say the mass that we have up top, this was representing our mass, and our mass was 250 kilograms. And we talked about datum earlier. Now this here is going to represent our datum. So this is just our ground that we're going to fall to. So just think of this as a fixed point that we're going to be falling to. So if we consider then our datum to be of some height like that, then at this point here at the very top right there, when our 250 kilogram is not moving, then our potential energy will be at its very most highest. So what that means for us is our total energy is just going to be a measure of our potential energy, which is mass times gravity times height, plus our kinetic energy at this point, because we're stationary, will be 0. Now, let's say for some reason we start to have some movement. So remember now that at this point, the only form of energy that we have is our potential energy. And because we're static, we have zero kinetic energy. But let's say for some reason, this 250 kilo mass, it falls some height, whatever that height is, half the distance or whatever. I'm not going to assign any value. So let's say it falls somewhat. So it means it will have some velocity falling. So we have some movement. So we now have some form of kinetic energy involved. So our total energy now, I'll put TE for total energy, would be some measure of our potential energy. And the higher up we are, the more potential energy we have. So the more mass we have falling from a higher distance. So what that means is some of our potential energy as we fall now will be going across to our kinetic energy. So we will have now another energy to sum up here. So we'll have some potential energy, so that's mass times gravity times height, plus some kinetic energy as we fall. And what's going to happen is as we fall closer to the ground, the moment just before, like let's say microseconds before we hit the ground right there, then what's going to happen with our total energy is it's going to virtually be zero for the potential energy at this point. The vast majority will be our kinetic energy, which is half mv squared. So you can see where it's quite a reversal, where at the very top we started off with maximum potential energy right there, but as we get closer to the height being zero, we end up with zero potential energy. And our kinetic energy will be at its maximum, because that's when, let's say, the object then would pick up some significant amount of pace. Let's think of it that way. So what that means now, if we look, the one thing that's constant is our total energy. So our total energy is always going to be a sum of the potential energy and the kinetic energy. And let's see what happens when we sort of relate the two now. So if we have mass times gravity times height, okay, so that's our potential energy there, we can actually relate it to our kinetic energy, which is our half mv squared. And what's going to happen here is typically we can use this formula to work out stuff like the final velocity, that sort of thing. Because if we were to just simply cancel out the masses, so divide both sides by mass, then what we're left with here is just gravity times height equals half v squared. So if we want to work out either the height or the velocity, any of these, then let's say we're doing the velocity, then our final velocity is just going to be the square root of 2 multiplied by gravity multiplied by height. So for those of you who have just skipped to this section, this is just a quick recap, not to go over in depth, but the long and short of it was that our potential energy plus kinetic energy, that should give us our total energy. And our total energy is going to be a constant value when we sum these two at any point, because as we fall from the top right there down to the bottom, at the very top we'll have maximum potential energy, and at the very bottom, when just before we hit the datum there, then our potential energy is going to be zero, and it is going to be the reverse for our kinetic energy, whereby at the very top before we start moving, then our kinetic energy is zero, and just before it hits the ground, then it's going to be maximum, and maximum meaning the same as what our potential energy was. So let's work out our potential energy now, just to see what our velocity is going to be. So as a start, we'll need to find what our h is, what our height is, and we'll just apply a bit of trigonometry. So if you can imagine that's being our opposite, this is our hypotenuse. So to find our opposite side, which is our h, then we can just say h is equal to the hypotenuse, so that's a 10 meter, multiplied by sin, and the angle is 10 degrees. So therefore we get h value of 1.736 meters. So now that we have our height, we're going to now use this to evaluate what our potential energy is. So our potential energy being mass times gravity and multiplied by height, we know our mass to be 250 kilo, times by gravity 9.81, and times by the height that we just calculated. So we get a potential energy here of 42 or 4,257.54, and this is going to be in joules. So we could have just written this as 4.3 kilojoules. Now let's evaluate now what our final velocity is going to be. So based on what we just talked about, where the potential energy, it's just translating into kinetic energy as it falls. So therefore our maximum value here for potential energy that we just got, which was the 4,257.54, that will be equal to our kinetic energy just before it hits the ground. So then that's our kinetic energy formula, our half mass times velocity squared, just as we have done previously. So what we want to do here now, we just want to rearrange this. So if we just get this as v squared first of all, equals our 2, which is in the denominator here, multiplied by our 4,257.54, and that will be divided by our mass of 250. So we get v squared equals, so that's 34.06, but of course we don't want v squared, we want the velocity, so we have to square root that now, and that gives us 5.84, and our unit is meters per second. So that gives us the final velocity there. Now I've used this same concept to apply to a bit more of a challenging question that you always get on engineering courses. It's using the conservation of energy principle, and you can check this video out right here if you'd like to learn more about this topic. So I'll see you in the next video.